Hello and welcome to my first video concerning the issue of whether the earth is round or flat. I first encountered this phenomenon of people claiming that the earth is flat maybe about a year ago, and to be honest, I genuinely just thought it was a joke. But the more I looked into it, the more I found that there are people who genuinely believe the earth is flat. It's quite shocking in this day and age that someone would believe that, but never mind, they do claim that they do. So what I want to do is just go through some basic mathematics and looking at the mathematics of the round earth and what reasons why we should believe that the earth is round. Now hopefully you can see what I'm doing here. I'll zoom in and out over the course of the video. Now you can see I've already started with a circle drawn here to represent the earth. Now we know that the earth isn't an exact sphere, it's a spheroid, but we can model it reasonably well using a sphere. So we'll just assume that the earth is a sphere, a perfectly smooth surface, just to make things simple. We know it isn't, but on a large scale it almost is. Now, I'll draw a line from the centre up like this. And we'll call this radius r. And we'll draw another line. Well, wait a minute. First of all, what I'm going to do is work out how you calculate how far the horizon is if you're standing on a sphere. Now, we won't start with the earth. We'll just start with just saying a sphere. So we've just got a person. Obviously, that's nowhere near the dimensions of the earth, but we can calculate, we can find a formula doing this that can be used for anyone standing on any sphere, okay? So, now, if someone was standing on top of a sphere like this, you can see that there are parts of the sphere that they wouldn't be able to see. They wouldn't be able to see the underside of the sphere down here or down here, okay? They wouldn't be able to see all this bit around here. They would be able to see here, and they'd be able to see here. So there's a limit to how much they can see. Now we call that limit the horizon. So if that's the person's eyes there, you can see that there's a line from their eyes that just touches the sphere, like that. Now I think you'll agree that anything beyond this point here, they're not going to be able to see it. Okay, they can see everything here, they can't see anything past here. Now, if I draw another line from the centre out to the point where that line just touches, that's another radius, so we can call that length r as well. Now, those of you that remember your high school mathematics will remember that a tangent is at right angles to a radius on a circle. Now, this line's a tangent because it just touches the circle at one point. This is a radius. Know that this is a right angle here. Okay. Now, there are actually two different ways of thinking about the distance to the horizon. You can calculate as the distance from the person's eyes, or the distance from their feet along this arc here, this curved part. Now, I'm going to calculate the distance from the eyes to the horizon, simply because it's an easier formula, and I want to keep things as simple as possible. It's fairly easy to calculate that bit as well. Now, if someone's height is small relative to the sphere, it doesn't make much difference. They're almost exactly the same anyway. They give you the same answers. Now, suppose we say that the person's height is h. Okay. Now, all I'm going to do here is use elementary school mathematics that you would learn when you're about 13 years old. It's nothing particularly complicated. Now, those of you that will remember your school mathematics will remember the theorem of Pythagoras, which is related to right-angled triangles. Now, if we call the distance from the eyes to the horizon d, then we can use Pythagoras to work out what d would be given r and h. Okay. Now, if you remember the theorem of Pythagoras, it says that the length of the hypotenuse squared, that's the longest side, is the sum of the squares of the other two sides. Now, this side here is h plus r. So we can write that as, put it as r plus h. I hope you can see that. Now that equals r squared plus d squared. Okay. Nothing particularly complicated going on there. I'll zoom in here a bit so you can see this derivation nice and clearly. Now, I can rearrange that. If I rearrange that, I get that d squared equals r plus h squared take away r squared. And then I get that d squared equals, sorry, not d squared, d equals the square root of r plus h squared take away r squared. Okay, so that's our formula. I'll zoom in on that so you can see it. That's our formula that tells us if you're standing on a sphere, a perfectly smooth sphere with a radius of r, and your eyes are at a height h above the surface of the sphere, the distance to the horizon will be given by the square root of r plus h all squared minus r squared. Okay? Not a particularly complicated formula. Now, I don't think there's anything particularly difficult or anything I've shown there. It's all quite elementary stuff. I'll just put it on there so you can see it. So I've just shown you a formula for calculating the distance from a person's eyes to the horizon if they're standing on a sphere. Okay? Now, I've represented the sphere as a circle, but a circle is a cross-section of a sphere, so the formula holds for a sphere. I don't think there's any problem with that. Right. Now, look at another formula. Let me draw a circle first of all. So, if I draw that there, and turn them around, get a nice circle. Okay, there we go. And the centre is there. Okay. Now, what I want to work out here is, if you were standing on a sphere and there was a vertical structure where you are, a distance away, another vertical structure will be an angle to where you are. Now let's have a look at this. So again, if I draw a line like that, and I draw another line there, you can see that this vertical structure here will be at a different angle to this vertical structure here. So both lines are vertical in their own location, but they're at an angle to each other because they're on a sphere. So we want to work out what's the angle going to be between them. So the angle will be there, x degrees. Okay. Now, supposing they're at a distance d apart. Now, d is an arc, it's a curved line. And again, we'll say that the radius is r. So the r is the distance from here to here. And it's the same distance from here to here. Okay, so we want to get a nice formula to tell us what this angle x is going to be. Now, again, this is fairly basic mathematics. You would learn this at school, like mathematics of this level. If we do a fraction of x over the number of degrees in a full circle, 360 degrees, that's going to be the same as d divided by the circumference of the whole circle. Remember, the circumference is the distance all the way around, so that's going to be that there. Okay. I'll zoom in so you can see it's a bit clearer what I'm doing. Now, I can write that as x squared over 360 degrees. Now, the circumference of a circle is 2 pi r. Now, if I rearrange this, we get x degrees equals 360 d all over 2 pi r. And if we cancel, we get that x degrees equals 180d over pi r. Okay, so that's a nice little formula that tells you what the angle would be between two vertical structures a distance d apart on the surface of a sphere. Okay. Now, what I want to do here as well is make a point that it seems lost on an awful lot of people who believe the Earth is flat. I'm not quite sure what the problem with it is, but it's quite a basic mathematical idea, okay, which I can demonstrate by drawing a circle. So now I'm going to do it fairly light, because I want to rub it out. Okay, so you probably can't see it that well, but I've drawn a circle there. Okay. Now, what I'm going to do is zoom in on a bit of the circle here. So it's not, right. What I'm going to do is I'm going to mark off 2 points on the circle, like that. Okay. Then what I'm going to do is I'm going to rub out the rest of the circle. Now I'll put my finger on that so I'll rub it out. So I'll zoom out. You can see me rubbing out this circle. And I'll see there's nothing funny going on. And again, I'll put my finger there so I won't rub it out. And what I want you to do is have a look closely at this. See how close I can get to it. Keep it in focus. Let me see. Sorry about this one. Now look at the little bit between the 2 points. Okay. It looks like a straight line. Okay. This is to demonstrate a very elementary mathematical idea, which is curves are locally straight. A curved line is locally straight. Similarly, a curved surface is locally flat. So if this was a sphere and I cut out a little circle in it, that circle would be almost completely flat if it was small enough. Now, it's a point that just seems completely lost on an awful lot of flat earthers. Like I said, I don't really get why, but it's such a simple idea. But I've demonstrated quite clearly. I mean, you can see that I've shown you this. A curved line, a little bit of it on its own, looks straight. So curves are locally straight. Now, one of the difficulties flat earthers seem to have, and to be honest, I almost sympathise with this point because it seems almost contradictory, but they always say, well, if you're standing on a sphere that's as big as having a radius of 4,000 miles, which the Earth has, how could a horizon be so close by? And if the horizon is so close by, surely you would see the curvature of the Earth. Surely you would see the Earth curving away from you. Well, the difficulty with that is that it doesn't really take into account the scale. Now, if I go back to my original picture here, okay, I mean, that's a person standing on a sphere that's obviously much, much smaller than the Earth. Now, the question is, how small would a person be on this diagram? Well, let's see, how big did I make this, the radius of this? So I don't know, say call it 9 centimetres, roughly 9 centimetres, okay? Now, so this has got a radius of roughly 9 centimetres. Now let's say we want to represent Mount Everest on this diagram, okay? How big would it have to be? Well, the radius of the Earth is taken to be 4,000 miles. So R is taken to be 4,000 miles. Okay, let's go down here. Everest is about So this might be a mountain, but it's meant to be, I think it's about 6 miles high. So if we do 4,000 divided by 6, we'll do it on a calculator so you can see I'm not cheating. 4,000 divided by 6 equals, I'm sure some conspiracy theorists will make something out of that, but it's about a 600. Say it's about a 600th, okay? So if I do 9 divided by 600, that gives me 0.015. That's 0.015 centimetres. That's how big Everest would be on this diagram. That's about 100th of a centimetre. I couldn't even represent Everest on this diagram. It's so small compared to the size of the Earth. If this was the Earth, a representation of the Earth, if this was a sphere with a radius of 4,000 miles, I couldn't actually physically draw Everest on here. It would be too small. Okay? It's very, very difficult to visualise how small we are on the face of the Earth. It's very difficult to visualise how far away the horizon should be for us, because our eyes are almost exactly on the surface of the Earth. We're only a tiny, tiny amount above the surface of the Earth when you're standing next to the sea. And it's difficult to visualise it. I agree with it. It is difficult to visualise, but we don't have to, because we've got the maths. So first of all, let's work out how far away the horizon would be. So let's look at the formula I had again. So the formula was D is the square root of R plus H squared minus R squared. Now, I'm actually going to do it in metric because it's just easier for the calculation. So it's 4,000 miles. Now that's, so 4,000 times 8 divided by 5, that gives you 6,400 kilometres. That's the radius of the Earth. Now if you're standing on the ground, let's just assume your eyes are a height 1.7 metres above the ground, which is 0.0017 kilometres. Okay? I'll show you those figures so you can make sure you can see them. Okay. I think I'm drawing a little bit squint for you. Okay, so let's bang those numbers in. So we get that D is the square root of 6,400 plus 0.0017 squared minus 6,400 squared, which gives you, do the calculator, so we've got square root of 6,400 plus 0.0017 squared minus 6,430 squared, close bracket, equals, done it wrong, well, I'll do it again. Right, I need two brackets, right, 6,400 plus 0.0017, close bracket, squared, minus 6,400 squared. There you go, 4.7, shall we call it? 4.7 kilometres. If you prefer miles, that's, I can divide that by 8 times by 5, that's 2.9 miles. Okay, so the mathematics is telling us, here it is, you can see it yourself, nothing fancy going on here. If you were standing on a perfect sphere with a radius of 4,000 miles and your eyes were about 1.7 metres off the surface of the sphere, you would see a horizon 2.9 miles away. Okay? Now, let me see, if I drew a line, okay, let me draw a line, say, make it 15 centimetres, okay? Now 2.9 is about 3 miles, so say call it 3 miles, make it easier, right? 3 miles. Say I want to represent that line as being a 3 mile long line, and I say, okay, so how big would a human being be on this line? Well, it's easier, I find it easier doing metrics, so wait a minute. So we'll do 3 times 8 divided by 5, so about 4.8 kilometres. Well, I said 4, that doesn't make much difference, right? So 4.8 kilometres, and a person their height is 0.0017, okay? So let's do 4.8 divided by 0.0017. Got 4.8 divided by 0.0017 gives you, what does that say? 2,800, roughly 2,800. So the distance to the horizon is about 2,800 times the height of the person's eyes above the ground. Okay? So next time someone says to you, well, the horizon's not very far away, how can it not be very far away? Well, it's 2,800 times further than how high your eyes are above the ground. Okay? Now, again, I can't even represent on this diagram how small a person is. It's very difficult to visualize these things because the scales are so difficult to deal with. Now let's consider, say there was a vertical structure at each end of this, one, so they're 3 miles apart. Well, let's figure out what would you expect the angle to be between two vertical structures? Well, x degrees, nice easy formula, 180d over pi r. Okay? So, I don't know, let's stick to miles. So say it's 180 times 3 all over pi times 4,000. What does that give you? Okay, well, 180 times 3 divided by 4,000 pi, 0.04 degrees. That's less than a 20th of a degree. Okay, there's the maths. Less than a 20th of a degree. Two vertical structures, 3 miles apart. Now, okay, let's get that in perspective. Let's think, what is a 20th of a degree? Well, here's a protractor. Let's see if I can zoom in on this. You see how small 1 degree is? You see it? That's 1 degree. Okay? So we're talking about a 20th of that. 20 times smaller than that. You would not in any possible way be able to detect that with the eye, with the naked eye. It's negligible. So although it seems slightly counterintuitive, this is what the mathematics tells you. If you're standing on a sphere with a radius of 4,000 miles, your eyes are 1.7 meters above the sphere, you will see a horizon line about 2 miles away, and the amount that the sphere will have curved away from you over that 2.9 miles is a 20th of a degree. So what you see basically is effectively, if you're standing on that sphere, what you see around you is basically a circle, a flat circle with a radius of about 3 miles. That's what you see. Now, you won't see vertical structures in the distance sloping at a distance. If it was on water, you wouldn't see ships turning through an angle as they go over the horizon. If you saw a hot air balloon rising in the distance, it wouldn't be rising at an angle to you. You wouldn't see it. The maths tells us that. Now, let me zoom out a little bit here. Another peculiar thing that you often hear from flat earthers is this thing say, oh, well, the horizon's flat, the horizon's flat. Without really qualifying in any way what they mean, what they expect to see if they were standing on a sphere, and not giving any real argument about that at all. They just go, oh, that's flat. Well, what do they expect to see? Do they expect to see it curve away from you noticeably in the distance? Well, no, it doesn't. We've shown that it doesn't. It will not noticeably curve away from you when you're standing at the seashore. You won't see it. So why would you expect the horizon to be curved? Well, what they really mean is the horizon forms a giant circle around you. Now, it's true, if you were standing on a circle that had a radius of maybe, say, 10 metres, of course you would see that it was a circle, you would see it curved. But why would you expect to see it if it's a circle with a radius of 3 miles? Now, this is also where a flat earth argument that just completely this doesn't work, because it can be doubled back on against flat earth arguments, because most flat earthers agree that if you're standing on an infinite plane, an infinite flat plane, that you will only see in any direction about 3 miles or 3 miles of that plane. Whatever reason they give for it, I mean, it's utter nonsense. There's no optical reason whatsoever why you would only see 3 miles if you're standing on a plane. There's none whatsoever. It doesn't mean anything. There is no law of perspective. But let's run with it. Okay, so they're suggesting that if you're standing on a flat plane, that what you see around you is a flat circle with a radius of 3 miles. So what you would see according to flat earthers is pretty much exactly what you would see if you were standing on a sphere with a radius of 4,000 miles. Just a flat circle around you with a radius of 3 miles. So if the horizon should be flat on, if the horizon should appear curved on a round earth, it should also appear curved on a flat earth. Now, the reason when you go up high that you start to see the curvature is not because the earth significantly curves away from you. You're still only seeing a tiny bit of it if you go up to, say, about 10 miles. I mean, they say you can start to see it about 10 miles, I've heard. I don't know exactly what it is, but now if you're 10 miles above the earth, let's just do a calculation. So the distance to the horizon is square root of 4,000 plus 10 squared minus 4,000 squared. Plus 10 squared minus 4,000 squared, close brackets, 283 miles. That's how far away the horizon would be. If you're 10 miles above a sphere with a radius of 4,000 miles. Let's calculate the angle that the Earth would have, or the sphere would have turned through or sloped through in that time, which is the same as that calculating what the angle would be between two vertical structures 293 miles apart. So it's 180 times 283 divided by 4,000 pi, which is 180 times 283 divided by 4,000 pi, 4 degrees. Okay, 4 degrees. That's how much curvature you would see even if you were 10 miles high above a sphere. 4 degrees. Okay, let's see if we can get this in focus. Sorry. There you go. 4 degrees, that amount there. You would see that amount of curvature over 283 miles. So you would still effectively just be seeing a very large flat circle around you. But the reason you see that it's a circle is because your eyes are quite far above it. That's why you start to see that it's a circle, not because you can noticeably see the curving of the earth. Now, let me see. If you may want to object to the arguments I'm making in this video. Well, I've thought about this and I can think of 5 main objections you could make. Okay. One is formulas are wrong. Formula's wrong. Okay. Well, if you want to show that these formulas I've shown you are wrong, you've got your work cut out. They're elementary school mathematics. They use well-established mathematics. One of them uses the theorem of Pythagoras. So really, if you want to show that that's wrong, you're going to have to show the theorem of Pythagoras is wrong. As I say, you've got your work cut out there for you. 2, formulas correct, not applied properly in some weird way. Somehow I've done it wrong, or somehow the mathematics, although it's right, it's somehow if you apply it to our situation, the maths goes haywire and gives all kinds of weird results. Well, again, you've got your work cut out there. I really don't know what you think could be going wrong, but I mean, I showed you very clearly what those formulas are, where they come from, and I showed you how to calculate things using them. So why would you think that it doesn't apply to us? 3, formulas correct. That's not an apostrophe there, is it? Formulas correct. Application correct. But Earth's still flat. So what you're saying in this one is that I've done everything right. I've shown what you'd expect to see if you were standing on a sphere, and it is pretty much what we do see, but for some reason you're still insisting the Earth is flat. Well, you're going to have to show me why. Okay, 4th one. Formulas correct, application correct, but not what we see. So you're saying that in this one, so I'll make that right. So you're saying in this one that the formulas are correct, the application is correct, and I have indeed predicted what you would expect to see if you were standing on a sphere with a radius of 4,000 miles. But it's not what we actually see on this planet. We don't see ships disappearing over the horizon if we're standing at the seashore about 3 miles away. Well, what do we see then? Explain to me why, if this is your position, explain to me what we do see. Question, objection 5, to use one of the flat earthers' favourite words, I'm obfuscating. I'm bamboozling you with complicated mathematics, and I false-suited you somewhere, and I've done something too complicated, and I've buried some false step underneath a pile of difficult mathematics, and I bamboozled you. Well, to be honest, if that's your situation, all I could say is you don't have the intellectual capacity to even have an opinion about this. This is really simplistic stuff. So if you think what I've shown you is too complicated, why do you even have an opinion? You really should just keep out of it. You're not smart enough to even talk about this. So if you want to reply to this video, you're perfectly welcome to. I'd like you to tell me which one of these positions you're taking, or perhaps another one I've not thought of. So are you thinking, have you got a problem with the mathematics? Have you got a problem with what you actually see on the earth? Or do you think I'm obfuscating, if that's the right word? Well, I look forward to your weird and wonderful replies.